Okay, recording is started. So as an introduction, I'm Scott Carey. I'm the Chief Engineer of Applications and Customer Support for Sugars International. My experience with Sugars was as a customer for over 9 years, working for the Amalgamated Sugar Company and Beet Sugar. And then I left Amalgamated and joined Sugars back in 2015. So it's been several years now that I've been working with Sugars International. So today we're going to talk about modeling boilers in Sugars and go through an example and explain exactly how that works. The first thing that most people that get familiar with Sugars probably will notice is that Sugars does not have a single station called a boiler station, and that's okay. It just means that we need to use a little more creativity to model a boiler in Sugars. However, what Sugars does have is 3 different boiler station groupings that are built in and are included with the program. And what that means is that the boiler can be modeled by a series of existing Sugars stations put together in the right configuration. What I've got showing on the screen right now, of course, is a blank Sugars model open in Visio. There's nothing here yet. And on the left side of the screen, you can see the Sugars stencils that open automatically when you open a Sugars model. Within the equipment-miscellaneous stencil, at the very top of the list are the 3 boiler station groupings. Okay, and as I said, those are built in with the program, and when you install Sugars, those stencils are installed, or those station groupings are installed with this stencil. The 3 types of boilers basically cover, obviously, Bagasse Boiler by its name. You can tell what that is. Boiler 1 would be a little more general, simplified boiler, and Boiler 2 is a little more complicated, but still more of a generalized boiler. So the most complex of the 3 and the most flexible of the 3 is the Bagasse Boiler. So that's what we're going to go over today. And if you learn to model a Bagasse boiler, then the other types will be pretty simple. If you're burning coal or natural gas or any other fuel, you'll be able to understand how to do that. So the first thing, of course, if we're going to use a station grouping, is we'll just grab it, drag it, and drop it onto our model. And you can see how large this one is. It's a pretty sizable grouping. So as soon as I let go of my mouse button, the first thing that happens is Sugars asks me for a station number. And of course, anytime you drop a station onto a Sugars model, the first thing you have to do is give it a number. My default setting is to start with station number 100 on a blank model. So I'm going to go ahead and allow that to be the number for this first station here. Click OK. Now you notice immediately, before I can do anything else, another station ID request dialog pops up. And the reason for that is by dropping a station grouping onto a Sugars model, we've actually dropped a whole series of stations onto the model at the same time. So Sugars is simply stepping through those stations, asking for station numbers for all of them before we can move on and do anything else. Now typically, and we've talked about this I think in maybe one of the 5-minute tips or something previously, but typically I like to leave space between my station numbers in a Sugars model, so that if the first one was 100, I might use 110 for the next one, so that there's room in between to go back and add more stations without having to renumber all the stations through the process. And that way I maintain my consecutive station numbering through the process. However, in the case of a station grouping, the strategy is a little different, because chances are you're not going to come back and add any stations intermediate to a station grouping. This grouping is designed to operate as it is, so I'm not going to be adding more stations inside the boiler grouping. So since my first station number was 100, it's okay to let the next station number be 101. So all I have to do is click OK. The next one after that, 102. And just let Sugars step through the stations, numbering them with an increment of 1. There's nothing wrong with that in this case. So I'm going to go ahead and click OK. And as you can see in the background, the stations that are being assigned numbers are turning blue, and the one that we're waiting on a number for is red. So you can see as you click OK which station you're numbering. I'm going to go ahead and go through all of them. As you can see, it's quite a group here. Okay, and that was the last. So now we have stations numbered starting with 100 right here on this pump, all the way through 115 on this distributor station up here at the top. And by the way, I'm just zooming in by using my control and mouse wheel so that it's quick and easy. Now, of course, all these stations are blue now. That means that they need names, and we'll get to that. But the first thing we have to do, as with any sugar station, is connect all of the required input flow streams and output flow streams so that the station has what it needs to balance. So I'm going to come over here to the Home menu in Visio and come to the Connector tool. Okay, we're going to start with the feed water. The feed water connects to this pump station right here, number 100. Now, because it's water, I like to assign it to the water and condensate layer. So I just came to layers, and I'm assigning it to the water and condensate layer, and that automatically turns it blue. And then I think I'll come here and add a label. So I'm going to click off there, click the text tool. I'm going to label this stream so I can see what it is. Feed water. Okay, so this will be our boiler feed water stream to supply the boiler. Now we need to specify this stream because it's an external flow coming into the model. We need to enter some things. I double-clicked on it to bring up the external flow properties dialog box. First, we need to give it a flow stream name, feed water, pretty simple. And in this case, right now, we're going to go ahead and give it a flow rate. And later, we'll talk about a case where you might not need to enter a flow rate for this. But for right now, we're going to give this 90,000 kilograms per hour. And we're going to call it 99 degrees C and 101.3 kPa, in other words, 1 atmosphere. And it's 100% water. We don't really need to enter any other components because it's all just water, and because there's no non-sugars or sugar, we don't need to worry about solubility coefficients, color, any of the rest. If you had a cost for feed water that you wanted to track, as far as water treatment or anything like that, you could enter a value here and then use the revenues report and sugars to track that cost. But for now, we're just going to say that it's 100% water. We've given it a temperature, a pressure, and a flow. Okay, the next flow stream in that we need to connect is the Bagasse fuel, which connects right there to receiver station number 111. So I'm going to go ahead and I think I'll just use copy and paste to put a label on that one. Copy, paste. Just double clicked and type in the new label. And I'm going to go ahead and go to layers and assign the bagasse to the product layer. That's not going to change the color, but in case later I wanted to change the color of all product streams, I could do it all at once for all of them belonging to that layer. Okay, so those are the only two input flow streams that we need to add to the boiler grouping, the feed water and the bagasse. Then we have two output streams we need to add. First one being, I'm going to go to the connector tool, and up here at the top, we have the steam leaving the boiler. And I'll go ahead and add that one to the steam and vapor layer, which will turn it red. And again, I'm going to go to the text tool. Oh, sorry, I have to click off. There we go. This would be steam. And lastly, we have the ash leaving the boiler. So back to the connector. And actually what I'm going to do this time, a little shortcut, I'm going to go ahead and just copy and paste the bagasse stream so that it's already on the product layer, which is what I wanted that ash to be on anyway. And then I can copy and paste the label as well. Okay, all of our streams are connected. I don't think I specified my bagasse yet. So we need to double click because this is another external flow coming into the model. We need to specify the properties of the bagasse. First thing, of course, is a name, bagasse. Now, the flow quantity is going to be calculated by the station grouping. It's going to tell us how much bagasse is needed to make the steam that this boiler is going to make. So I'm going to leave the flow quantity at 0 on the bagasse stream. Not necessary to enter any information there. The temperature, we'll make it 61 degrees C. Pressure, of course, is atmospheric. Bagasse will just be on a conveyor of some sort. It's not under pressure. And then we need to set the components of this bagasse. So first of all, we're going to say it's 50% water, okay, 50% moisture bagasse. Most of the rest of bagasse would be comprised of fiber. In this case, we're going to use 47.8%. And then we're going to add 1.6% sucrose. And now we need to finish the last amount of this bagasse with non-sucrose number 1. And just so I make sure I get this right, I'm bringing up my calculator here. So 100% minus 50% water minus 47.8% fiber minus 1.6% sucrose equals 0.6% non-sucrose number 1. And it's critical that all the components add up to 100% when you're specifying an external flow stream in sugars. And if they don't, sugars will pop up with a warning message telling you that you need to fix it. But in this case, I just used the calculator to make sure I got it right. You can give color if necessary, but in this case, color is not interesting to us for bagasse. But we will need to select solubility coefficients because now we have sucrose and non-sucrose present. So I'm going to come to the solubility coefficients and just use typical cane values. It really doesn't matter in this case because we're not going to be crystallizing any sugar in the bagasse boiler. And lastly, as we mentioned earlier with feed water, and it's probably even more important with bagasse, if you wanted to assign a value to that fuel per kilogram, you could do that here, and then the sugars revenue report would account for the use of it in the overall net revenue. And again, that may be even more important if you're setting up a coal-fired or gas-fired boiler using a purchased fuel. Okay, so our bagasse is now specified. All the temperature, pressure, components, and again, we're leaving the flow rate at 0, which is telling sugars that it's okay to manipulate that as a required flow. Okay, so our input external flow streams are specified, feed water and bagasse. We don't have to specify anything for our ash or our steam because sugars is going to calculate the properties and flow rates for those streams as they're leaving sugar stations. Now what we have is the task of specifying the parameters for all of these internal stations within the grouping. So we're going to go ahead and start with this first feed water pump right here, station 100. I'm going to zoom in a little bit so you guys can see a little better. And I double click to bring up the pump properties dialog box. Now the first thing that we have to do is give it a station name. First feed water pump. And then we're going to give it a pressure. Now this is not the final boiler drum pressure that we're indicating here. This is more of an initial pressure to represent the feed water supplying the main feed water pump. So this would be to a deaerator or something of that nature. In this case, we're going to use 300 kPa for the pressure out of this pump. And notice that it turned yellow because now it has a station name, and you'll see that as we go through all the stations. Okay, the next station in line here is a blender station. I'll double click it. The purpose of this blender is to control the temperature of the feed water before it's pumped to the drum. So we'll call this the feed water temperature control. And what we're going to use this blender for is to set a desired outlet temperature of 130 degrees C. And what it will do is here from the final steam distributor at station 115, it will blend steam back to the feed water to achieve this temperature. It'll control that steam flow to control the temperature out of the blender of the feed water. Okay, that's all we need to do there. Now we come to the actual boiler feed water pump that supplies the boiler drum. So I'll go ahead and double click on station 102 there. It's another pump. And in this case, this is where we will set the final high pressure steam temperature, or steam pressure, excuse me, that the boiler achieves. In this case, we're going to use 2,900 kPa. But that would be whatever your boiler pressure actually is. Oh, and we need to give it a name as well. So feed water pump number 2. Okay. All right, so now we have the feed water up to pressure. The next station is a separator station. However, actually no separation takes place in this station. So this is one of the first sort of tricks of modeling boilers and sugars. So I'm going to go ahead and double click on this station. And what I'll call this station is the Bagasse feed water ratio. The purpose of this separator station, again, is not to separate anything, but it's to ratio two flow streams while keeping them separate. So what we want to do here is we want to bring in Bagasse, which is the black flow stream coming in input port number 1 on the side here, and the feed water, and we want to control that bagasse flow at a certain ratio to feed water without mixing the two. So the bagasse comes in this port 1 here and leaves port 1 right out the bottom, while the feed water comes in port 0 up here and leaves port 2 on the side over here. So they're not mixing, but we're using the separator to ratio one flow to the other without mixing them. Now, what's the value for this ratio? Well, that's a question that's going to be specific to every boiler that you model. And it's simply determined by the basic amount of, the average amount of fuel required per mass of steam produced. So it's a mass ratio. In this case, we're going to use 0.5 just to make the math easy. But you need to determine that value based on the actual performance of your boiler and its efficiency and the energy content of your fuel and all the rest. So it's not a simple answer to that value, but it does rely on the ratio of fuel consumed to steam produced in your boiler. That's what we're entering there. And what we need to specify also is that all of that, in this case it's bagasse, but it's diluent for a separator, all of it needs to go out port number 1. So 100%. That ensures that none of the bagasse actually mixes with the feed water in the boiler here. Over here on this side, we don't need to do anything because we're not separating any components out from any stream. So we leave all this alone. Okay, that's all we have to do for that separator station. Now, if all we were doing was burning a constant fuel, like a natural gas or even possibly a coal that's basically constant all the time, the fuel doesn't change, that separator would be the end of it and the fuel could leave as ash. However, bagasse is variable. It has variable moisture content, variable sucrose content, and therefore variable combustion energy. So this boiler grouping actually has ways to account for all of that. So what we're going to do, I'm going to double click on the next separator here, station 104. This separator has bagasse leaving the previous separator station coming into it, and it's being separated into two streams. What we're doing here is we're separating all the water out of the bagasse. So I'm going to go ahead and give this station a name. Call it gas water separator. And what we're going to do is simply take all the component liquid water, so all the water that's in the bagasse, 100%, and send it out flow output number 1. Nothing else goes out that output. So all the other components we leave 0. So what we're doing is we're taking all the water out of the bagasse and sending it out number 1, and leaving all the solids to go out number 2. And I'll explain why in just a second. So I'll go ahead and click OK. So that station is set up. Next one, I'm going to click here on station 109. This is a blender. What we're going to do with this blender is we're going to ratio a certain amount of bagasse to that water that we took out of the bagasse. And I'll explain in a second, but we're going to call it the bagasse water ratio. Okay. What this blender station does is it takes some fresh bagasse that came into station 111 and then to distributor 110 here, takes some fresh bagasse and uses it to account for the energy required to evaporate the moisture in the main stream of bagasse. So in other words, and this is another parameter that you'll need to determine specific to your boiler, but you need to find out how much the specific consumption of bagasse increases as moisture content increases, because obviously as moisture content increases, the energy content of the bagasse goes down. So this is a way that sugars can account for that. We're taking the moisture content that we separated in the previous station, and we're going to ratio the bagasse, a little bit of extra bagasse, to use up to evaporate that moisture. So in this case, this ratio, we're going to go ahead and use 0.005 to the total flow. Okay, so that we're going to use 0.005 tons of bagasse for each ton of water that was in the bagasse and was separated in the previous separator. Okay, all we're doing here is accounting for the moisture content and the extra energy required when there's high moisture in bagasse. So I'll go ahead and click OK. Quickly, while we're here, I'm going to go ahead and give these two stations names. There's no, so this would be bagasse distributor. There aren't any settings that we need to set here because both of these flows will be required flows, so we don't need to set any quantities, leave them 0. And this one, being a receiver, doesn't have anything other than the name, so. The gas receiver. Okay, so all we had to do for those two was give them names. I just wanted to do that while we were close. Okay, so going back to our bagasse process here, now we have station 105. Now, if you remember, from station 104, we separated the moisture into output number 1 and the solids into output number 2. So this is the bagasse solids coming down into separator station 105. I'm going to go ahead and double click on it and bring up the properties dialog box. The purpose of station 105 is to separate the sucrose out of the bagasse solids. So I'm going to go ahead and let's see here. There we go. I'm going to go ahead and give it a name. Bagasse sucrose sep. And now in this case, we're going to go to dissolved sucrose, and 100% will go out flow number 1, which would be here on the left. None of the other components will go that direction. So all of the other components will go out output number 2. Okay? We're taking all the sucrose this direction. Go ahead and click OK. Now we're going to account for the increased energy content of bagasse when the sucrose content is high. So I'm going to go ahead and click on the next separator station, station 106. Okay, this one is very similar to the separator station we used up here, 103, to ratio the total bagasse flow to the total feed water flow. But in this case, we're going to take a portion of the bagasse and ratio it to the sucrose flow that we took out in station 105. So right here, go ahead and ratio 2 times the amount of sucrose. And all of it needs to go out station 100 because again, all of it needs to go out flow stream number 1 because again, we're not going to mix the flows. So in this case, we're going to say that if the sucrose content is higher by a ratio of 2, we need to increase the amount of bagasse that goes from this diluent input number 1 to output number 1 and is recycled back. Okay, so by recycling it back, we offset bagasse that came in from external flow. By the way, I forgot to name this station here. I'm going to call this, let's see, bagasse sucrose ratio. Not quite enough letters there, but that's okay. So again, I just want to make this clear because it's a little bit tricky, okay? This is not a straightforward thing, but this is our way of taking the sucrose we separated from bagasse solids. It's going to come into this separator and go out port 2, okay? Because we're not separating anything from that stream out into output port 1. So all we're doing is making a ratio of the bagasse that's left to that sucrose flow and recycling it back so that it offsets fresh bagasse coming in from outside. And the reason for that is if the sucrose content is higher, we're going to get more energy out of that fresh bagasse. So that's what the recycle is for, is to account for that additional energy. Again, this ratio here is something you'll have to determine based on testing of your in this case, we're just using 2.0 for easy math, but you'll have to determine based on actual performance what that value would be in your case. Okay, I'm going to go ahead and click OK. We have a distributor station here. No settings required because, again, everything is going to be a required flow or calculated by sugars. So I'm just going to go ahead and say gas solids distributor. And the last is a receiver station down here that collects all the bagasse components that we separated out, moisture, solids, sucrose, back together into an ash stream for disposal. So go ahead and ash receiver. Just give it a name. That's all it needs because it's just a receiver station. All right. Now we have handled the bagasse all the way through from feed, ratio to steam flow, out to ash, okay? We still have to handle the steam side of the boiler because all the farther we got earlier was to the feed water and its ratio, or the bagasse flow ratio to the feed water. Okay, so the feed water was not separated or changed. It was just ratioed in this station 103. It came out output port number 2, and it goes on to distributor station 112. So we need to give that a name. I'm just going to call it feed water distributor. We don't need to specify any of the flow rates because those will be specified by sugars either as required flows or as excess flows from upstream. So we don't need to do anything there. The next station here, station 113, is a reactor station. And Reactor stations are generally, they're kind of rarely used in sugars, but when they are used, they're very powerful. In the case of a boiler, we're not actually accounting for a chemical reaction. Well, in a way we are. We're accounting for combustion. But the components coming into and out of the reactor are not what's burning. So I'm going to go ahead and name this station combustion. What we need to do in this reactor is convert feed water in its liquid form. So I'm going to go ahead and take the input flow component of water as a liquid, 100 mole percent, is going to convert to water vapor, in other words, steam, at 100 mole percent. Of course, this is 1-to-1 because it's water molecule for water molecule converting from liquid to vapor. Now, there's a reaction efficiency here, and ideally in a boiler it's 100%. We'll go ahead and use that. Anything less than 100%, you would end up with slightly less than 100% steam quality coming out of this reactor station. So you'd have a little bit of liquid water left in the steam, but in this case, we're going to use 100% reaction efficiency. And then we need to specify the heat of reaction. Okay, the heat of reaction is the enthalpy added to the steam by the combustion. It's not necessarily exactly the heat of vaporization. And the reason for that is because in most boilers, you end up with some degree of superheat in your final steam. So what the heat of reaction that you're looking for here is the actual heat added to the water, both in the process of vaporizing it and in the process of heating it. So in this case, we're going to use 2650 kilojoules per kilogram. But the best way to determine this heat of reaction is to try different values until you reach the steam temperature that you actually observe in the boiler before any desuperheating occurs. So that would be the best way to determine that value. Okay, so we've now set the combustion reaction in this reactor station 113. Okay, next station in line is 114. This is a blender station, and this one is simply to control the final steam temperature leaving the boiler. So I'm going to go, let's see, steam temp control for a name. And all we have to do is specify the temperature here. In this case, we're going to use 360 degrees C. What this blender station will do is look at the amount of feed water that has not been vaporized yet required to reduce the temperature of this steam to the specified temperature here. So it's going to take feed water from distributor station 112 as a required flow and blend it with the steam leaving the reactor station to reduce the temperature as a desuperheater, in effect, down to the temperature you specified. That's all we need to do with this station is specify the temperature, click OK. Now the last station that we have that's still blue is a steam distributor here. And for right now, I'm not going to specify any flows because I'm going to let them be calculated by sugars, be whatever they need to be based on other stations. So I'll just, let's see, live steam distributor. I'll give it a name. Click OK. And now all of the stations in the grouping, go ahead and zoom out here so we can see all of them. One more. They've all got names and specifications. So we've given every station in the boiler grouping a name and a specification. Okay, before we do anything else, I want to make it so we can see some of the parameters. So I'm going to go to the flow streams, and most of you are probably familiar with this, but in case you're not, I'm going to right click and come right here to add flow legend, top of the list. Click on that one, and sugars gives me a list of parameters that I can display on the model drawing, and they'll be updated every time we balance the model. So for feed water, I want flow rate by weight, the pressure, and the temperature. And that data now is displayed on the screen. I'll go ahead and do the same for bagasse. However, for it, I want the weight, but let's take the temperature. But I think I want the amount of water and the amount of fiber, and probably sugar as well. And you notice it got tall enough that it moved the flow stream a little bit, so I'll just drag it down so everything straightens out again. Okay, we can do the same for ash. Weight, temperature, water, sugar, and fiber. And for steam, weight, pressure, temperature. And I'll go ahead and drag that over here. Okay, so now when we balance our model, we'll be able to see the flow rates and components that we've called out here on the drawing surface. All right, so I'm going to come to my sugars menu here at the top. And since I've already specified all the input external flows, and I've specified all of the stations within the station grouping, I think I'm ready to balance. So I'm going to go ahead to the red button here and click full balance. You notice it turned green. That means that the model is now balanced. I did not get any warnings or error messages. So that means that everything within the station grouping is working okay. So let's take a look at what happened. We have 90,000 kilograms per hour feed water coming to the boiler. We specified that in the external flow stream dialog. It was at 1 atmosphere, 99 degrees C. And the steam that's being produced is the same amount because we did not separate any water from the stream, the feed water within the boiler station grouping. It all ends up in the steam as it comes out at the specified pressure, which we specified in the feed water pump, and temperature, which we specified in this blender station 114 here near the end. So that all looks good. The bagasse flow, 45,927 kilograms per hour, was calculated by sugars based on the ratios that we entered in these separator stations. And that depends on the water content, the sugar content as well, because there were ratios to account for those. It's interesting that the ash flow is slightly higher than the bagasse flow. I suspect that difference is due to the model tolerance that we have set in this balance, because there's really no separation going on. Those should not have been different at all. It's within 1 kilogram, or just over 1 kilogram per hour, so less than 1. Anyway, so one thing I wanted to demonstrate, because of the way that we set up the ratios for the different components, let's say that the bagasse water content goes up by 2%, so 52% here, and the fiber content goes down by 2%, so 45%, or 5.8% here. Okay, now we've changed something, so the balance is no longer, the model is no longer balanced. Okay, we haven't changed the feed water or the steam, basically the heat requirements at all. We've just increased the water content of the bagasse. So let's rebalance. Okay, and the difference is slight, but the bagasse flow did increase because it requires more bagasse when the water content is higher, therefore the heat content is lower. Okay, another thing we can do is come in and increase the sucrose content by 2%. So let's make that 3.6. And now the fiber is going to drop to, actually let's take it out of water. Let's take it back to 50% water. So this should cause a significant reduction in bagasse requirement because we decrease the water content and increase the sucrose content. Both of these will drive the heat content higher. I'm going to go ahead and balance the model again. And yeah, that one took over 1,000 kilograms per hour off of the amount of bagasse required to produce the same amount of steam. So that just demonstrates how all these separators and ratios work to account for differences in bagasse components and content. And of course, in a factory-wide model, you could connect this bagasse stream to the milling or diffusion or whatever portion of your model is set up. So it actually brings in the actual properties of that bagasse as it's produced. Or if you had bagasse in storage, then maybe it would be constant like we've got it here. That just depends. One more thing I wanted to demonstrate is, let's say that we want to account for steam demand and have the boiler supply whatever steam is demanded. Okay, so we may have a process out in the factory, or a whole ton of processes that are using steam. So I'm going to come here to miscellaneous shapes, and I'm going to go ahead and add a distributor station to this model. All right, so that's station 215. Let's make it station 220, just so we had lots of room. And I'll go ahead and connect the steam to its input. I'm going to give it a name, steam header. And I'm going to go ahead and just copy and paste this steam flow stream so it's on the correct layer already, and I don't have to do that again. And there we go. We'll go ahead and just move this label over. Now I could, if I moved this flow legend over here, it'll stay there, that's no problem. But I really shouldn't do that, because now it's referencing the flow stream that's back over here. So what I should do is go ahead and delete that flow legend, right click, create a new one on that flow stream so that we're certain to get the right information. Now in this case, of course, with only one input and one output from a distributor, they would all be the same anyway, but you might add more flows later and forget that you didn't create a new flow legend here. So it's always good practice. Anytime you want to move a flow legend to a different stream, delete the old one and create a new one based on that new stream. Okay, so here's what I wanted to do is let's say that this steam header demands 100,000 kilograms per hour of steam. Okay, now I'm going to come back to the feed water, because now I want the boiler to determine how much feed water is necessary. So I'm going to take away the flow specification on the feed water input. Just leave it 0. Leaving a flow stream 0 tells sugars that, if possible, sugars should calculate that value. I'm going to go ahead and balance again. Okay, we got a small balance warning here. It's probably due to some of the recycle that goes on in the boiler. I'll go ahead and click OK. And a lot of times when that occurs, if you balance again, everything balances out fine, which is what just happened there. And the reason for that is in the preferences, we've got the number of iterations set pretty low in this balance because it's a small model. And so it just didn't have quite enough iterations the first time to get to a full balance. But when I balanced again, it iterated a few more times, calculated a few more times, and everything balanced out fine. And so what you can see here is that now, because we asked for 100,000 pounds an hour of steam demand in this header, the steam and all the feed water flows are now required flows back through the boiler, and the feed water is a required flow. And of course, it's within tolerance the same amount, not perfectly exactly, but that's within the balanced tolerance. So that's how you would normally set your boiler up in a factory model, where the processes are demanding a certain amount of steam and the boiler needs to produce enough to supply that. You use that, just allow those to be required flows, and sugars will calculate back to the feed water. And of course, the bagasse, again, is adjusted to supply the right amount of fuel based on all the ratios that we entered here. Okay, well, that's all I have for modeling boilers and sugars. Again, there are 2 other boiler station groupings in the miscellaneous equipment stencil. Neither one is quite as complicated as the Bagasse boiler. So if you understand and can model a Bagasse boiler, you can certainly model the other 2. That's why we focused on this one today. Before I wrap up, I just wanted to open it up if there are any questions. Please feel free to ask. You can use the chat window in GoToMeeting here, or if that doesn't work for you, just speak up. Don't forget to unmute your mic if you're speaking. Okay, well, I don't see any questions coming up, so I just want to say thank you very much for participating, and we really appreciate all of your interest and having all of you as Sugars users. We will, of course, post this recording on our YouTube channel, and I believe we'll be sending out an email with a link to that in case you want to refer back to it. This Bagasse boiler grouping example is actually in the sugars example model called cane factory milling. So if you're interested in that, you can look at that boiler. I didn't model it exactly the same as that example today, but pretty close. So if you're wanting to refer to that, you can. Lastly, just so those that are in the USA or maybe elsewhere and are planning to attend, I just wanted to let you know Sugars International will be at the ASSBT conference in Disneyland here in just about a month, and I'll be giving a talk on performance curves using sugars. So I hope to see you there, or if not, hope to see you at our next webinar. We'll be probably setting up another one within a few months. So thanks again. If you have any questions, don't hesitate to contact us. We're always here to help, and we'll see you again in the future. Thank you. Bye.